Good day. So in this video, I'm going to show you some examples involving simple matrix operations. The presumption here is that you have already read through the slides and probably some of the sections in the assigned textbook. So what we're going to do here is we're going to solve some simple matrix operations as what's shown in the module 1A of matrix algebra. So there are we're just going to present some of the operations that would be necessary later on in the exercises that we're going to do in the subsequent sessions. So for now, we're going to stick with some numerical examples of how to solve or how to execute some basic matrix operations. And we're going to escalate this and discuss further the implication or the functionalities of these matrices when we talk about system of linear equations. So to start, let's begin with the simple addition and subtraction of matrices. Now, take note that you can only add or subtract matrices that have the same dimension. So, for instance, A and B have the similar dimension. So both of them are 2 by 2. In a sense, you have two rows and two columns, right? So if they have the same rows and the same number of rows and columns, then we can add and subtract each of the elements. So if, for instance, I ask you to solve for A plus B, or it could be A minus B, that's the same. Um, since they have the same dimension, they have the same number of rows and columns, we can easily do the operation. So element by element, we'll just execute the addition. So that's going to be 0 plus -1. So that's -1. And this is going to be the second row, first row, second column. You have -2 plus 4. So that's going to be +2. And for the second row, first column, second row, this is going to be 3 plus 1. It's going to be 4. And then you have 1 plus 5, that's going to be 6. Okay. Now, we cannot do the same, or we cannot do the same for C and D, since C and D have different dimension. So in any case that you wanted to find A plus C, that matrix would be undefined, right? Since they don't have the same dimensions. The dimension of a matrix is essential not only in the simple operation like this, but also in matrix multiplication. Okay? So we cannot multiply matrices. We cannot get a product of two matrices if their dimensions are not the same. Specifically, if the number of rows of the first matrix is not equal to the number of if the number of columns of the first matrix is not equal to the number of rows of the second matrix. And having said that, it's evident that we don't have the commutative property of multiplication for matrices, since changing the order of matrices when you multiply them will yield different things, or one of the products could also be undefined. Now, for simple operations such as addition, okay, so you've seen this already. Now, what if we wanted to, say, multiply a matrix with a scalar? A scalar meaning you have a matrix that has a 1 by 1 dimension. In other words, just a constant. So for instance, if I wanted to multiply this matrix with some constant alpha, say we multiply this with some constant alpha, then you just have to distribute it. You can easily do that by distributing alpha across all of the elements in the matrix. So this is going to be, let's construct the matrix here. This is going to be 1, -1 times alpha. So that's negative alpha. And this is going to be 2 alpha. This is going to be 4 alpha. And this is going to be 6 alpha. At this point, it's fairly simple, right? Now, of course, we cannot do the same operations anymore for C and D since they have a different dimension. Now, what if you wanted to get the transpose of the matrix? Okay? So what if you're asked to get the transpose what if you want to get the transpose of a matrix? So the notation for transpose is either a raised to t, sorry, a raised to big T, but later on, to avoid confusion, you're better off using using prime. So you just you indicate a prime. So to get the transpose of the matrix, you just have to basically switch the rows, and the rows to columns and columns to rows. Or to be specific, you just have to pivot the row column, the row vectors into column vectors within each matrix. So the diagonal will remain the same. So this is the diagonal of your matrix. The diagonal of the matrix stays the same, and you just have to pivot the rows, right? So in the case of A, the transpose of A would be 0, 3, -2, and 1. So there's a rotation. So you basically rotated the rows to column, okay, and column to row, right? So you did a rotation. For B prime, the transpose of the matrix is, and by the way, in later applications, we'll be focusing on square matrices like A and B. For this for mathematical modeling, non-square matrices like C and D are rarely used. Probably in econometrics, fine, but in mathematical models, in linear economic models, you would likely encounter 2 by 2 or 3 by 3, usually square matrices, because they're easier to work with. Now, if I'm going to get the transpose of B, that's going to be -1, and this is just going to be 1. This is going to be 4, and this is going to be 5. So the diagonals are intact, right? You just have to switch the non-off diagonal elements. Now, what if you have a non-square matrix like matrix C? So to get the transpose of C, okay, if this is a 2 by 3, so two rows and columns, so two rows and three columns, so you have 2 by 3 matrix. The transpose of C should be a matrix with a dimension of 3 by 2, so three rows and two columns. Okay, so it's gonna look like this, something similar to D. So to get the transpose, the diagonals are the diagonals are intact. In this case, the diagonal or the corners will be intact. So you have 8 and 4, okay? And then rotate the rows into columns. So this is going to be 3, this is going to be -2, and here you'll have 1, 1, and 0. Now for D, since D is a 3 by 2 matrix, the transpose of D should be a 2 by 3 matrix, something similar to matrix C. Okay, so the dimension here would be 2, 2 rows by 3 columns. Okay, um, so you'll just have to rotate this. Okay, you'll have to rotate this. So endpoints pa rin. Just the endpoints, the 2 and -5 will remain intact. Okay, so this is going to be -5, and then rotate the columns into rows. So this is going to be 2, 4, 1, and then this is going to be -2, 3, 5. Okay. So that's the rotation. Now, you already have in your notes the distinction between a matrix and a vector. Now, x is a vector. Now, just for demonstration, let's add another vector here. Let's define vector y as, say, another vector. Okay, so let's denote it as 0. Let's say that this is 0, -2, -2, and 3. Okay. Now, in your notes, I showed you how to get the transpose of a vector. So if you wanted to get the transpose of a vector, which is very applicable in some applications of or in solving linear equations, right? So X transpose would just be a row version or a row vector corresponding to, or the equivalent row vector of X. So that's going to be 0. Uh, let's add some placeholders here. It's going to be 0, negative 2, and 4. Okay. And then Y would be, the transpose of Y would be equal to 0, negative 2, and 0, negative 2, and 3. Okay. Sorry, let's add the transpose here. So I'm pretty sure that this is going to be very easy when you apply this to other types of matrices. You just have to remember that the diagonals for square matrices, the diagonals will stay intact, and you'll just have to rotate the off-diagonal elements. For non-square matrices like C and D, just watch out for the corners, right? Basically, that seemingly diagonal corners of the matrix that will, and then you'll pivot. You'll pivot the corresponding rows about that endpoint. For for vectors, it's fairly simple. You just have to convert it into their corresponding rows. Or if the vector is defined as a row vector, you just have to convert it into a column vector. Now, for more complicated, a little bit more challenging uh, exercise, let's try getting the inner product of vectors, which is a precursor to solving products of matrices, which is in, I think it's in your, oh, it's not in slide 3B. But getting the getting the inner product of two vectors is a really nice starting point to get the products of two matrices. Now, take note that the dimension of the vector and later on the dimension of the matrix is essential in getting the product of the two. So for instance, you have a vector x, like so. If you have a vector x, 0, negative 2, and 4, and you have vector y whose elements are 0, negative 2, and 3, okay, you cannot just get the product of x, y because their dimensions do not correspond to each other. In other words, the number of rows, in order for matrix multiplication to happen or vector multiplication to happen, the number of the number of rows, the number of rows of the first, the number of rows, sorry, the number of columns rather, the number of columns of the first vector should correspond to the number of rows of the second vector. Okay. So for instance, we have x, y. Let's try that x, y. So if we try to get the product of these two, we get the product of these two vectors. So you have 0, negative 2, you have 4, and then you have 0, negative 2, 3. Okay. So you cannot do this because, well, the number of columns of the first vector doesn't correspond to the number of rows. So you have one column here, but you have three rows here. So that's not possible. And this attempt to multiply these two vectors would be impossible, right? Well, not unless that you have something like this. So if for example, you wanted to say multiply the transpose of x, which is the row vector of x times y, you'll get what you call the inner product of two vectors, right? And we just copy this, transpose y. Oops. Okay, so notice here that the number of columns, now correspond to the number of rows. Right? The number of columns correspond to the number of rows. So to get the inner product, and later on we will use this when we try to get the product of the matrices. To get the inner product of two vectors, make sure that their dimensions are matching. So this is a three. This is a 1 by 3. This is a 1 by 3 vector. The second vector is a 3 by 1. It's a 3 by 1 vector. Since the number of columns match the number of rows, we can do the multiplication. And doing so, we have 0 times 0 plus or minus 2 times negative 2 plus 4 times 3. Okay, so the first term disappears. You have positive 4 here, and you have positive 12, so you have 16, right? So the resulting inner product would always be a scalar. Now, you can also do the same for x, y transpose. Okay, so x vector is a column vector as defined, and then we multiply it with a row vector. Okay. So notice here that, well, number of rows, still you can still multiply this. So you have the number of rows here. The number of rows, so you have 3 rows, corresponds to the number of columns. So you have one row here corresponding to one column. Okay, so you can still multiply these two vectors. So what would be the resulting output? So the output here would just be a 3 by 3 matrix, because you're multiplying a 3 by 1, multiplying a 3 by 1 vector with a 1 by 3 vector. So the resulting matrix would be a 3 by 3 matrix. So how will you do the multiplication, or how is it possible to why are we going to get a 3 by 3 matrix? Well, you'll multiply the first row. You can multiply the first row with the first column. Since it's just one element, 1 is to 1 element, unlike this one, unlike the second example, which is in all aspects would be wrong. Okay, so you just multiply the first row with the first column, so it's going to be 0. Multiply the first row with the second column to get the second column value for the first row. So that's 0 times negative 2, that's going to be 0. And of course, 0 times 3, that's going to be 0. For the second row corresponding to this, so you have negative 2 times 0, it's 0. You have negative 2 times negative 2, it's going to be 4, positive 4. And you have negative 2 times 3, that's negative 6. And for the last row, which is 4, so multiply this 4 times 0, it's 0. You have 4 times negative 2, it's negative 8. And then you have 4 times 3, that's positive 12. Right? So dimension matters. Right? Dimension matters. And the dimension of your matrices, or the matrices that you're trying to multiply, will determine later on the dimension of the product of those two matrices. Okay. Now, what if we try to multiply a B? Okay, what if we multiply matrix with a matrix, or let's start off by multiplying a matrix with a vector. Okay, let's have a new slide and just copy the examples here. Okay. Let's copy the given. Okay, let's change the layout. Go to text, copy this here, and then let's reduce the file. Let's reduce the font size. Okay. Now, what if I ask you to get the product of A and X? Okay, is this even possible? Obviously, it's not because, well, you have a 2 by 2 matrix here and you have a 3 by 1 vector, right? The number of rows of X exceeds the number of columns of A. So AX is not possible. Right? Same goes for B, right? So B times X is not plausible. Right? It's not plausible because, well, the number of columns of B doesn't match the number of rows of X, so you cannot do that. But we can do the same. We can do the operation for CX, right? Because the number of columns of C correspond to the number of rows of X. So if we're going to get the product of C and X, okay, C times X is going to be, for demonstration purposes, let's copy this matrix here. We'll copy this matrix, we'll copy this vector, right? This is a 2 by 3. This is a 2 by 3 matrix, and you have a 1 by 3, or sorry, you have a 3 by 1, have a 3 by 1 matrix, and so you're going to get a 2 by 1, 2 by 1 vector, a 2 by 1 matrix. Okay, so let's insert the placeholder here. We're going to get a 2 by 1 matrix. Why? Because if I multiply this, right, if I multiply this first row with this column vector, I'm going to get 8 times 0 plus 3 times negative 2 plus or minus 2 times 4. Okay? So each element of the row vector times the E times all of the elements in your column vector. Okay? Same goes for the second row. So that's going to be 1 times 0 plus 0 times negative 2 plus 4 times 4. Okay. So the corresponding matrix, 2 by 2 by 1 2 by 1 vector to be specific, would be, so you have 8 times 0, it's 0, you have negative 6 minus 8, so negative 14, and this becomes 1, 0, 0, 4 times 4, you have 16. Okay. Now, of course, you can switch sides, or if you try to switch X and C, again, matrix multiplication is not commutative, so you cannot just switch matrices or vectors. Right? You cannot just switch their places because you're going to get a different answer. Okay, or if anything, the solution might not even exist because of the dimensions of your matrices. Now, what if we try to multiply two matrices? So if we try to multiply AB, right, that's going to be the product of 0, negative 2, 3, 1, this matrix times this matrix. So this is a square matrix. This is a square matrix. So you have the same dimensions. This is a 2 by 2. This is a 2 by 2. So the resulting matrix should also be a 2 by 2 matrix. Okay. So let's add a placeholder. So this becomes, you get the product. You get the product, or the sum product of the first row and the second column. First row and the first column. So that's going to be 0. 0 times negative 1, 0 plus negative 2 times 1, negative 2. So it is negative 2, right? So if you have 0, negative 2 times the row column vector 4, 5, right? So you'll have negative 10. Okay, so you have the second row, first column, so that's negative 3, plus 1, and that's negative 2, right? And then you have the second row, second column. So 3 times 4, 12, plus 1 times 5, 5. So that's going to be 17. Take note again, just to prove that matrix multiplication is not commutative. If you try to get the product of B times A, you're going to get a different answer. You're going to get a different answer. This is easy to verify with square matrices like this one. Later on, when you try to multiply C and D, you will find out that while one of the products may exist, the other one won't, right? Because of the different set of dimensions. So this becomes, you have 1, 4, 0, 0. This becomes 12, right? So the objective here is that by the end of the course, or as you go through your program, you should be comfortable multiplying matrices, right? Or you should be at least comfortable picturing out the dimensions or picturing out the operations in your head, right? So you have first row, first column, so that's 0, negative 1 times 0 is 0, plus 4 times 3, that's 12. Okay, so here, in the first element alone, you can see that AB is definitely not equal to BA because you have a different first element, right? So first row, second column, so you have positive 2 plus 4, so negative 1 times negative 2, 2, plus 4 times 1, 4, so you have 6, right? Then you have 1 times 0, 0, plus 5 times 3, 15. And then you have 1 times negative 2, negative 2, plus 5 times 1, 5. So you have 3. So A, B, and BA are different. Of course, they are matrices. There are special matrices that are yielding the same answer, right? There are special matrices that will yield the same answer regardless of their order, one of which would be the identity matrix. If one of them is an identity matrix, say for instance, if let's define the identity matrix as I2, I2 refers to the number of rows and columns, right? And identity matrices are only applicable for square matrices. Okay, so suppose you have 1, 1, 0, 0, right? Regardless of the order of the matrices, the resulting product will still be the same. So AI2, you can verify this. AI2 is basically equal to I2A. In the realm of matrices, the identity matrix is your equivalent of 1. Right? So you multiply anything with 1, you'll get the same number, right? You get the same scalar. In the case of matrices, you multiply any square matrix with an identity matrix. Regardless of the order, you will get the same. You'll get the same matrix A. Okay? You can try this yourself. Now what if you wanted to multiply C and D? Okay? Now, if I wanted to multiply C and D, so CD would be equal to 8, 3, negative 2 times 2, 4, 1, negative 2, 3, 5. This is possible. This is possible because the number of columns of the first matrix C matches the number of rows. Okay? Number of columns must match the number of rows. You just have to remember that. Now, to solve this, the resulting matrix would be, so this is a 2 by 3 matrix. This is a 3 by 2 matrix. So the resulting matrix would be a 2 by 2 matrix. So the end points, basically, the number of rows, the resulting matrix would be, the dimension of the resulting matrix would be the number of rows of the first matrix and the number of columns of the second matrix. So you have 2 rows here, you have a 2 by 3 matrix here, and you have a 3 by 2 matrix. Okay? And that will yield a 2 by 2 matrix. So this is equal to 8 times 2 plus 3 times 4 minus 2 times 1. Okay. For the second column, first row, second column, this is going to be 8. So notice first row, first row, first row, first row times second column. So that's going to be 8 times negative 2 plus 3 times 3 minus 2 times negative 5. Now for the second row, this second row and first column, this is equal to 1 times 2 plus 0. You have a 0, so this is going to be easier. 0 times 4 plus 4 times 1. Okay. And lastly, you have 1 times negative 2 plus 0 times 3 plus 4 times negative 5. Okay. So you have a 2 by 2 matrix. Okay. You have a 2 by 2 matrix, and solving the or executing the operations, you'll get 8 times 2, 16 plus 12, 28 minus 2, so that's 26. Right? 8 minus 2, 26, yeah. So you have here negative 16. 16 turns to negative 13 plus 10. So you have negative 3. You have here 2 plus 4. You have 2 plus 4, 6. Right? And here you have negative 2 minus 20. So you have negative 22. Negative 2 minus 20. So negative 22. Now, if you try to switch this, two matrices, right? You'll get a different, or it may not even exist. So if you try to say get DC, right? What's the equivalent? What's the resulting product? No? So DC would be equal to this and this 2 by 3. Right? Okay. Well, true enough. Well, we're lucky enough to get something like this. So you have a 2 by 3 made. You have a 3 by 2 matrix and a 2 by 3. 3 by 2 matrix and a 2 by 3 matrix. So the number of you know that you're sure that you can multiply this because the number of columns correspond to the number of rows. So you have 2 columns, you have 2 rows here, so they can match. You can match the elements together, and then you'll get a 3 by 3 because you have 3 rows and 3 columns. So you'll get a 3 by 3 matrix. Okay, so let's add a placeholder. It is going to be a 3 by 3 matrix. Okay, so you just multiply this. So the first row with the first column, so that's going to be 16 minus 2. That's 14. It's going to be 2 times 3. The second term will disappear because of the 0. So you have 6. And for the first row, third column, you have negative 4 minus 8. You have negative 12. Okay. For the second row, so you multiply the second row, first column, so that's going to be 32, sorry. 8 times 4, 32 plus 3, so that's 35. You have another 0 here, so this is going to be 12. That's going to be 12. right? And then you have negative 8 plus 12. Negative 8 plus 12, that's going to be 4. Okay. Now for the third row, right? So you get the third row. So third row times first column. So that's going to be 8 times 8 times 8 minus 5. So that's going to be 3. Right? And then 1 times 3, the second row 0. So that's just 3. And then you have negative 2 minus 20. Again, you have negative 2 minus 20. You have another negative 22. So notice it is different. No? Again, matrix multiplication is not commutative. It's not commutative. It is associative, that's fine, but it's not commutative. Like you cannot just change the order of you cannot just change the order of the matrices. Okay. So in the next video, I'm going to show you in detail how to compute the determinants of the matrix and what will be the application. Oh, by the way, before we go through that, now having learned matrix multiplication and vector multiplication, probably it's about time for you to know how to convert linear system of linear equations in matrix form, right? So suppose you have this matrix. Suppose you have this system of linear equations. So x1 plus 2x2, right? So let's be specific. So you have x1 plus 2, so yeah, x1 plus 2x2 plus 3x3. And let's denote that as a constant, so equal to some constant a. Okay. And then suppose you have another here, which is x5, sorry, you have 5x1 plus 14x2 plus x3. x3 equals b, right? And then suppose you have x1 plus x3 equals c. Now, earlier, probably in your college algebra, you were asked to solve for a system of linear equations with the three unknown variables. That's actually difficult if you don't know how to use matrices. Now, knowing matrix algebra actually will make things a little easier to solve. No? So to convert this in matrix form, the elements of the matrix would be the coefficient of each variable. Okay? And the vector will correspond to x1, x2, x3. So this is going to be a 3 by 3 matrix because you have 3 equations and 3 unknowns. So this is going to be, oh, this is going to be of the following form. So, oops, sorry, this is a 3 by 3 matrix. Okay. So this is going to be equal to the coefficient. What are the coefficient of the elements? So it is going to be 1, 2, 3. You have 5, 14, and 1. Okay, and then you have 1. What if one of the variables are missing? So if one of the variables are missing, it just means that the coefficient of that variable is 0. So since x2 is missing in the third equation, its coefficient is just 0. And then you have 1. Now what happens to x? X now becomes a vector. Yeah. Becomes a vector of unknowns. So this becomes x1, x2, and x3. And the exogenous parameters a, b, and c would be another vector. So that's going to be a, b, c. So notice that if you execute the matrix multiplication, right, you will get your system. You will get your system of equations. So if I multiply the first row with this column vector, I'm going to get x1 plus 2x2 plus 3x3. If I multiply the second row with this column vector, I'm going to get 5x1 plus 14x2 plus x3. If I multiply the third row with a column vector, I'm going to get x1 and x3. Okay, so this is how you convert, and this is how you transform linear equations, system of linear equations in matrix form. Now, in your probably in your macroeconomics and econometrics, this will be very crucial. This is going to be a crucial exercise because it's going to be easier to solve aggregate output. In the case of macroeconomics, it's going to be easier to solve for the equilibrium output and interest rate in the ISLM model if you know how to transform that ISLM model in matrix form. Okay. And that is also essential in our later discussion when we talk about the inverse of the matrix. And I'm going to show you how to solve system of equations using matrix inversion. Okay. So that's gonna be our lesson in the next. That's gonna be our lesson in the next video.